Okay, so today we are in lecture number 7 in our series of discussions on probability and statistics for AI with focus on NLP. So today we'll spend some time on proof, step by step, just because this makes us, confident of what we are doing, and also maybe just for the beauty of the proof itself. So start with a motivating example. All cigarettes presently on the market have an average nicotine content of at least 1.6 milligram per cigarette. Now, nicotine is something we would like to avoid. A farm that produces cigarettes claims that it has discovered a new way to cure tobacco leaves that will result in the average nicotine content of a cigarette being less than 1.6 mg. So the farm claims it has been able to reduce the nicotine content. Now, to test this claim, a sample of 20 of the farm's cigarettes were analyzed. So this is the sample size of 20. If it is known that the standard deviation of a cigarette's nicotine content is 0.8 mg. So this is known from data which has been observed. What conclusions can be drawn at the 5% level of significance if the average nicotine content of the 20 cigarettes is 1.54? So a very typical scenario where we have to have some confidence in the property of the population, okay, and that is based on the sample that we have extracted from the population and are making observation on. Now, do remember that for us, population is the whole language landscape, okay? A particular language or maybe all the languages together. Hello? Hello? Any problem?
No, sir.
No? Okay. Screen is still visible?
Yes.
Yeah, okay. Okay. So all of you, please mute your mic if you're not speaking. So this is a very characteristic situation, and for us, do remember that in NLP, our population is nothing but the whole language landscape. Okay, all languages maybe, or maybe a particular language, maybe Konkani, maybe Assamese or French. So we would like to make claims about the behavior of the language, properties of the language, which we can make use of in building algorithms for doing useful tasks. Okay. So now in this case, the population is the whole set of cigarettes manufactured by the company. And the company says that it has improved upon the state-of-the-art performance. The state-of-the-art performance is that on an average, there is 1.6 milligram of nicotine per cigarette, okay? And that the company claims it has been able to bring down to 1.54 milligram, from 1.6 milligram to 1.54 milligram by applying some kind of procedure on curing the tobacco leaves from which the cigarette is made, okay? So isn't it very analogous to, let's say, me creating a new part-of-speech tagger, and the state-of-the-art part-of-speech tagger for this particular language, let's say, is 98%, and I claim my part-of-speech tagger has accuracy of 99%, an improvement of 1%, which has effect on downstream applications like, let's say, sentiment analysis, where I need to accurately detect the adjectives, first of all. The accuracy improves because I have an improved part-of-speech tagger. Okay, so this has implication. So I make this claim, And this claim has to be verified. It must hold for all the language situation on which my part of speech tagger will work. So I take actually an NLP application, and NLP startup claims that it has created an automatic speech recognition tool called Sun Rahahu. Hypothetical, suppose the tool is called Sun Rahahu. And this improves the state of the art. The best available commercial ASR has an average word error rate, okay, word error rate of 1.6 per sentence. I deliberately kept the number same as the nicotine problem. The word error rate is 1.6 per sentence, and it is known that the standard deviation of word error rate of ASR tools is 0.8. So you measure the accuracies of ASR tools, and you get word error rate of 1.6, 1.7 maybe, and 2.2, and so on. And you observe all this data and find out that the standard deviation of word error rate is 0.8. To test the claim of the startup, a sample of corpora of 20 organizations, again 20 corresponds to 20 cigarettes from the nicotine, from the company. 20 organizations were given to Sun Rahahu, the ASR tool, and the accuracy was observed. What conclusions can be drawn at the 5% level of confidence if the average word error rate of Sun Rahahu is 1.54 per sentence on the corpora of the 20 organizations? So this is the correspondence. The cigarette company said that it has been able to bring down the nicotine level. Out of the 20 cigarettes, I found out that the nicotine level is indeed 1.54. Okay, so it is really less than 1.6, which is the average nicotine level. But it is on a sample of 20 cigarettes only. Can I believe the company that the nicotine level has really come down for all the cigarettes that it manufactures? So same is the case of this ASR tool called Sun Rahahu, which brings down the word error rate in general. And currently, for 20 situations, the word error rate is 1.54 per sentence. So what claim can I make? How can I believe the performance of this ASR company? And can I believe the cigarette company? So all I have is the population average of 1.6, the sample average of 1.54, and the population standard deviation is known, which is 0.8. Okay, these are the numbers that are in front of me. So what can I do? What instruments do I have? So this is the start of discussion on testing of hypothesis, which will occupy us for the next quite a few lectures. Okay, we're going to do it slowly and theoretically establishing all the fundamentals. Now the theory is this. We first discuss the case of a known variance. Suppose x1, x2, x3 up to xn is a sample of size n from a normal distribution having an unknown mean and a known variance sigma square. So for the cigarette company, n was 20. I have taken 20 cigarettes and I am observing the values there, statistics there. We are interested in testing the null hypothesis that mu is equal to mu naught. Okay, against the alternative hypothesis, mu is not equal to mu naught. Now, null hypothesis, alternative hypothesis, these are very sacrosanct in testing of hypothesis theory. And our particular situation is that the nicotine content has fallen below 1.6. Okay, so we are interested in mu less than mu naught. So it is a special case of mu not equal to mu naught. Now, mu not equal to mu naught is called two-sided test. Okay, mu not equal to mu naught can be both greater and smaller. Now, our situation of nicotine content or word error rate for the ASR is a one-sided tail test. One-sided test. Okay, so we will go into those technical details, which is very fundamental for us, and you probably understand the motivation from what I described through part of speech tagger that I have created, or the company which has created a new piece of software, which is Sun Raha Hu. So this will be tested. Now, common sense or intuition tells me the following. From the sample, I have been able to, able to find out the average. Just a minute. I've been able to find out the average from the sample, and that is a point estimator for mu. Okay, so through the sample average, I would like to estimate mu. It seems reasonable to accept H0, the null hypothesis, if X bar is not too far from mu. So now, definitely it is not likely that the sample average will be exactly equal to population average, but we want it to be close to the population average. I do not know the population average. I know the population standard deviation. If I do not know the standard deviation also, then there are other techniques, t-test and so on, so which also is something we would like to do. Now, the problem is very clear. Sample average should be close to the population average. And therefore, we would like to introduce a notion of what is called the critical region. So this is the fourth term we are introducing: null hypothesis, alternate hypothesis, and critical region, and also two-sided test, one-sided test. So the critical region of the test will be C equal to x1, x2 up to xn such that x bar minus mu naught is greater than C. Okay, so so this is the test which will measure the distance between the sample mean and the population mean. Now, the sample mean and population mean can be for any parameter, by the way. Okay, so it can be the accuracy value. It can also be the probability of the noun phrase forming out of determiner and noun, on which we made some remarks a few lectures back. Okay, that I have a probabilistic context-free grammar rule, which says that NP goes to DT-NN with 0.5 probability. That means 50% of the noun phrases are composed out of determiner and noun. So this is a statistic, and the statistic being close to the sample statistic being close to the population statistic is always investigated through a critical region. Is the sample value close to the population value? So for that, we have a lot of mathematical machinery at our disposal. So I think we are making progress towards understanding the test of significance or hypothesis testing. So for this concept of region, that some probabilistic quantity is close to another probabilistic quantity, we have the mechanism. Okay, we have the mechanism of the standard normal variable and the area under that standard normal curve. Okay, so we can mark out the areas within the standard under the standard normal curve and see if two variables v1 and v2 fall within that region, in which case we can accept the hypothesis that v1 and v2 are close to each other. Okay, and the region which is outside that interval, that gives me the probability of error. Okay, so in particular, you will recall that from z equal to minus 1.96 to plus 1.96, the area under the standard normal curve is 95%. Okay, so for such a situation, the error region will be on both sides of minus 1.96 and plus 1.96. So that will be the error region, and the error region's area is 5%. Okay, so we can be sure of 5% error if we insist on 95% confidence interval being true. Okay, so this is our basic instrument. So two intuitions here. One is the sample statistic should be close to population statistic. The two parameter values should be close to each other. Now the meaning of close to is made more rigorous by invoking the standard normal curve and the area under that normal curve. Okay, and we know that 99% of the area would be from minus 2.54 to plus 2.54 under the standard normal curve, and that will ensure 1% error. So relating error to area under the normal curve is something which we can exploit for hypothesis testing. I think this intuition is something we would like to keep with us and go forward to develop the mathematical machinery. So can somebody verify that you are seeing notion of region as the slide?
Yes.
Yeah, okay. Okay, fine, great. So now we know how to how to deal with the area under the standard normal curve through z-score, and the z-score tables are given, which we know how to read. If I have 1.26, then I go to the row 1.2 and the column 0.06, and from there I read the probability table. I also know that that the area under 1.19, I can see from the z-score table is 0.8830. That means from minus infinity to 1.19, the area under the standard normal curve is 0.8830. Okay, so then let me summarize how we are proceeding. I know the population standard deviation. I know the sample mean. I assume normal distribution somewhere. Okay, normal distribution somewhere. Now, the distribution need not be normal always. That will be the first question that will arise in our mind. But for that, we have built a kind of ground by saying that if the number is large, then some quantities begin to behave like a normal distribution. Okay, and that ground we have been covering for some time now, last 4 or 5 lectures. Okay, and what is that ground? That ground is the central limit theorem, for which the proof will be completed today. Now, this notion of region and choosing sufficient number of examples so that this critical region can be ensured, where I decide the critical region before the investigation starts. And after deciding the critical region, I would like to know the value of n. How many samples I must look at? How many observations should I make? Okay, a statistician will be able to tell me how many cigarettes I should observe for the company. Okay, how many corpora I should observe for the ASR startup. So this methodology we have very well understood through the bridge example, which started our probability lecture. And I would like to again remind you of the main points of this example, because this is so analogous to the kind of questions that we are asking. So here the question being asked was, how many cars on the bridge will make the bridge unsafe? Okay, how many cars can simultaneously be on the bridge so that bridge does not break or equivalently, how many cars, minimum number of cars will make the bridge unsafe. So that we had dealt with by comparing two probability distributions. The total weight of the car, which is normally distributed, and the tolerance of the bridge, which is also normally distributed. And from that, we were able to get a value of n unsafe as to how many cars will make the bridge unsafe. And we applied the central limit theorem and got the mean and the standard deviation of total weight on the bridge when n cars come on the bridge. Okay, the means are added. The variances also are added. Okay, and the tolerance curve again has mean of 400 and standard deviation 40. So our condition was that total weight should exceed the tolerance level, both of which are normally distributed probabilistic variables. So equivalently, W total minus W tolerance should be greater than 0. Now, W total minus W tolerance also cannot be a deterministic statement, both of them being probabilistic variables. This quantity of W total minus W tolerance being greater than 0 also must be a probabilistic statement. And there again, I fix my threshold. Okay, I make that probability to exceed 0.1. W total minus W tolerance being greater than 0. So now, having formulated the problem, I apply algebra. W total minus W total tolerance being greater than 0, I subtract 3n minus 400. 3n minus 400 is the mean, okay, mean of W total minus W tolerance. W total's mean was 3n, W tolerance's mean was 400. The two normally distributed variables are subtracted, therefore their means are subtracted. Okay, so I have done this on both sides, and I'm dividing them by the standard deviation. Now, the two normally distributed variables have been subtracted, but subtraction doesn't affect the variance. Okay, variance are still added even though there is subtraction, whose proof we'll see in a moment. Now, standard deviation is square root of the variance. So I've divided both sides by the standard deviation. Now I am able to invoke the standard normal variable z. So the left-hand side of the inequality is standard normal variable z, and z should exceed this quantity, 3n minus 400, and divided by the square root. Okay, so I've come up to this by my algebraic steps. Now z is this quantity, W total minus W tolerance minus the mean divided by standard deviation. And the probability of z exceeding this quantity, which is equivalent to the total weight exceeding the tolerance level, that probability should be greater than 0.1. So this quantity V is something we are interested in, because that is what will yield the value of n unsafe. How many cars will make the bridge unsafe? Now, probability of z greater than V is equal to 1 minus probability of z less than V. 1 minus P is z less than V. You are interested in z less than V because z less than V is what is given in the z score table. Okay, so since we want probability of z greater than V to be more than 0.1, that brings us to probability of z less than V should be less than or equal to 0.9. Now, by consulting the table, z score table, I see that the probability of 0.9 under the normal curve happens when z is equal to 1.29. Okay, so now I have to equate 1.29 equal to that expression, which will yield me the value of n unsafe. Okay, and by solving this, I can get n equal to 117. And this tells me the final outcome. If we allow more than 117 cars on the bridge, then in 100 out of 1,000 such cases, the bridge will break. Again, you see that the statement is not really deterministic. I'm saying that the bridge may or may not break, but in 100 out of 1,000 such 1,000 cases where 117 cars are allowed on the bridge will break. Okay, so this is a very instructive example from Sheldon's book on probability. And if you look at probability lectures on YouTube or see the testing of hypotheses or this kind of situations being covered, many of them make use of this particular example. This example has really become famous because it illustrates the underlying technique so well. So, so two probabilistic quantities are compared and an interval, safety interval is found. And from that, the variable of interest and its value are found. So this is very nice to note. We should keep this technique in mind and should be able to use it in NLP work. Now we come to central limit theorem. The central limit theorem was invoked in two places for the bridge problem. When we wanted to know the total, the property of the total weight coming on the bridge. Okay, their central limit theorem was invoked. Another place central limit theorem was invoked was when we subtracted W tolerance of the bridge from the total weight on the bridge. So there also the central limit was invoked, but because we had to find out the mean of the quantity W total minus W tolerance. So again, central limit theorem was invoked. And we wanted to do all this so that we could make use of the Z score table. So central limit theorem, there are many equivalent statements, okay? And the actual formal statement, we have looked at informal statement of central limit theorem before. Now we give the actual formal statement. Let x1, x2, x3 up to xn be n independent random variables. Let Sn be the sum of those n independent random variables. Then the expectation of Sn is summation of expectations. This can be proved from the definition of expectation. And the variance of Sn is sum of the variances. Okay. Again, this can be proved. The proof for the variance I will do 2-3 slides later. So, so if you relate it to the bridge problem, then x1, x2 up to xn are the weights of the n cars. Okay, are the weights of the n cars. Or if it is the cigarette situation, then x1, x2, xn are the nicotine levels of n cigarettes. Okay, so this is the situation. And we are interested in the summation of these random variables, the values of these random variables. Now, let us deal with the variance a bit, because variance seems to be having a non-intuitive behavior. The variance of x1 plus x2 is addition of variances. Variance of x1 minus x2 is also addition of variances. Okay, so how come this is the case? Now, variance is defined as the expectation of difference from the mean and square of that. Expectation, the variance is the expectation of the square of the difference between the value of the random variable and the mean of the random variable. Okay, so variance is expectation of x minus expectation of x square. So variance of x1 plus x2 therefore will be expectation of x1 plus x2 square by definition, minus expectation of x1 plus x2 whole square. So expectation of x minus ex square, this by applying some algebra comes out to be expectation of x square minus expectation of x whole square. Okay, so variance is equal to ex square minus ex whole square. So variance of x1 plus x2 is expectation of x1 plus x2 square minus expectation of x1 plus x2 whole square. Now x1 plus x2 square can be expanded, a plus b whole square, x1 square plus 2x1 x2 plus x2 square minus expectation of x1 plus x2 is expectation of x1 plus expectation of x2. Okay, this is a theorem which we know. Again, we apply a plus b whole square and expand ex1 plus ex2 whole square. So when I have these terms, I see that 2 ex1 ex2 cancels from the two expressions, and then I have ex1 square minus ex1 whole square plus ex2 square minus ex2 whole square. So this is variance of x1 plus variance of x2. Now let's look at the variance of x1 minus x2. By definition, this is expectation of x1 minus x2 square minus expectation of x1 minus x2 whole square. So apply a minus b square whole square, x1 square minus 2x1 x2 plus x2 square. And expectation of subtraction is subtraction of expectations. So expectation of x1 minus expectation of x1 x2 whole square. So I expand by a minus b whole square once again. And then I find that this 2 into ex1 plus ex2 again cancels from the two expressions. So I'm again landed up with ex1 square minus ex1 whole square plus ex2 square minus ex2 whole square. So this is again variance of x1 plus variance of x2. So independent of the sign, the variance of sum or subtraction of a set of random variables is nothing but the sum of individual variances. Okay, so an intuition for this should be built up. So you should really think about why variances get added up while means get subtracted. Okay, this is a question which I think I have asked you before also. So keep reflecting on this, why variances are additive. Okay, now we come to the central limit theorem statement. Let x1, x2 up to xn be n independent random variables, each with mean mu and variance sigma square. So mu and sigma square are also the population mean and sigma square. Also let Sn equal to this sum. Then the statement of the theorem is that Sn, this summation is normally distributed if n is sufficiently large. And if all these x1 to up to xn are themselves normally distributed, then there is no restriction on the number of n. Okay, so Sn is normally distributed. And more importantly, which is useful to us because we can make use of the z-score table, this Sn minus n mu divided by sigma root n. Okay, the standard deviation of Sn is sigma root n because n sigma square is the variance of Sn. Standard deviation is n sigma square root over. So that is sigma root n. And the mean is Sn minus n mu. I'm making the mean equal to 0. So Sn star is also normally distributed. Moreover, its mean is 0 and standard deviation is 1. Therefore, Sn star is a standard normal distribution. So this is the statement of central limit theorem. It is saying that some of these random variables are also normally distributed. In particular, what is of use to us is Sn minus n mu divided by sigma root n is a standard normal distribution. Okay, so that is the theorem and that needs to be proved. So I hope you are understanding the crux of the theorem. The crux of the theorem is Sn minus n mu divided by sigma root n is a standard normal variable. And that needs a proof. So now we can look at the other statement of central limit theorem, which is also famous and frequently used. So I take Sn star equal to Sn minus n mu divided by sigma root n. I do a bit of algebra. I divide numerator and denominator by n. Then I have Sn by n minus mu divided by sigma root n by n. Now Sn by n is nothing but the population mean. Okay, so the n variables have been obtained and they are divided by n. So this is nothing but the population mean. Mu is the, not population, sorry, sample mean. and mu is the population mean, divided by sigma by root n. Okay, sigma by root n. So this quantity is also normally distributed with mean 0 and standard deviation 1. This is the alternative statement of central limit theorem. What is that theorem? What is that statement? Let x1, x2, x3 up to xn be n independent random variables forming a sample from a population with mean mu and variance sigma square. Then the sample mean is normally distributed with mean mu and variance sigma square by n. Okay, these two statements are equivalent. You apply the statement as per the problem situation. Okay, so with this statement, let me read again. If x1 to xn is a sample from a population with mean mu and variance sigma square, then the sample mean is also normally distributed. Sample mean is also normally distributed with mean mu and variance sigma square by n, or standard deviation sigma by root n. Okay, so in the bridge problem, which version of central limit theorem we used? We used the summation version. Okay, sum of the random variables is normally distributed with mean n mu and variance n sigma square. For the bridge problem, we use that version. But there will be problems where we will use the other version of the central limit theorem, whereby we say that the mean, sample mean is normally distributed with mean mu and standard deviation sigma by root n. Okay, this is the other version. But I hope you have been able to see the equivalence between these two statements of central limit theorem. Okay, do keep that in mind. One version is with the summation, the other version is with the mean of the sample. Okay, so let's proceed. To prove this central limit theorem, which we have to finish today, we have to invoke another very powerful concept from statistics and probability, that is the moment generating function. So this is the definition of moment generating function. Let x be a random variable. Then the moment generating function of x is mxt, where t is introduced for the purpose of moment generating function. So you're looking at moment generating function slide, right? Can you please verify, somebody? You're looking at the slide?
Yes,
Moment generating, yeah, okay. So mxt equal to expectation of e to the power tx. So I do not, I have the random variable x, okay? I do not deal with x directly. I multiply x by t, which is the moment generating functions building block. And I raise t into x to the power e, to the power of e. And expectation of e to the power tx is called the moment generating function. Why the moment generating function is in this form? So we'll understand as we go along. Now, the expectation is defined, expectation of a quantity is defined as the probability mass function into that random variable with j going from 1 to n, where j varies over all possible values of xj. So the random variable here is capital X. It takes values small x1, small x2 up to small xn. So j goes from 1 to n. I am interested in the expectation of e to the power tx. So I take e to the power txj multiplied by the probability mass function of xj. Okay, probability mass function of xj will be same as the probability mass function of e txj. So, so this is the definition of expectation. And if I am dealing with the continuous random variables, the continuous distribution, then the summation is replaced by integration, going from minus infinity to plus infinity, where fx dx is the probability density function of the random variable, and e to the power tx is the quantity I'm interested in. Okay, so this is the moment generating function for a random variable. Discrete random variable, first expression, continuous random variable second expression. So let's see what this moment generating function gives us. But before that, there is another powerful theorem called the uniqueness theorem. Suppose x and y are random variables having moment generating functions mxt and myt respectively. Then x and y have the same probability distribution if and only if mxt equal to myt identically. So that means if the moment generating functions are identical, then the underlying probability distributions also are identical. Okay, so this is called the uniqueness theorem. We would like to look at the proof of uniqueness theorem also at some point of time. But as we go along, I think we appreciate the mathematical skill, mathematical genius of people who have created this kind of knowledge for use of many other disciplines. Okay, so uniqueness theorem establishes one-to-one correspondence between moment generating function and the underlying distribution. If two moment generating functions are same for two random variables, then the random variables must be identically distributed. Very, very, very powerful statement. And the moment generating function itself in this form as expectation of e to the power tx is also a mathematical ingenuity. So while engineers devise, ingenious instruments, the theoreticians devise ingenious theoretical and conceptual machinery. Okay, theoretical conceptual machinery come from our mathematicians, physicists, theoreticians, logicians, humanities, social scientists, political scientists, psychologists. They give us conceptual instruments, and engineers conceptual and useful instruments. Engineers devise useful and ingenious machinery. For example, the steam engine, aeroplane, the computing machinery, and so on. Computing machinery is engineers' invention. The supercomputer is engineers' contribution. But the underlying Turing machine concept, a simple finite state head moving over an infinite tape, that is a conceptual machinery, so elegant and so simple. That comes from a mathematician, Alan Turing, computer scientist. Okay, this is conceptual machinery. So as engineer, we must appreciate both the technological ingenuity and scientific and humanities ingenuity. In particular, in natural language processing, we have to appreciate all science, engineering, humanities, everything. So now, these moment generating functions being equivalent make the underlying normal distributions equivalent. So now we have got, just 1 minute, there is some noise outside. Okay, am I audible?
Yes.
Yes, sir, you are.
Yeah. So the slide you are seeing is delving into MGF, correct?
Yes. Yes.
Yeah, okay. So moment generating function is expectation of e to the power tx, and in particular for continuous distributions, this is integration minus infinity to plus infinity e to the power tx fx dx. Fx is the probability density function of x. So why this moment generating function is important, and why is it called moment generating function? So I take the first derivative of moment generating function. So derivative of mxt dt is derivative of expectation of e to the power tx. This is expectation of x e to the power tx. How can this derivative go inside expectation? If you expand the expectation as a summation of PMF into the value of the random variable, and since derivative distributes over summation, this is valid. Okay, so derivative of expectation is expectation of derivative, and derivative of e to the power tx is x e to the power tx. Let me take the second derivative also. When I take the second derivative, I get expectation of x square e to the power tx. So this kind of taking derivative is pretty general with respect to the nth derivative. For nth derivative, the nth derivative of the moment generating function is x to the power n e to the power tx. So this is important for us because I see that if I put t equal to 0, then I get e to the e expectation of x on the right hand side. So the mean of the random variable is the first derivative of the moment generating function at t equal to 0. Okay, this comes in very, very handy when we want to find out the expectation of a random variable and we know the distribution of that random variable. So when you want to find out the expectation of a random variable, you have to take summation over the different values of that random variable multiplied by the PMF, or you have to integrate the product of the random variable value and the PDF. Many times it becomes very cumbersome. Okay, that integration or that summation becomes cumbersome. On the other hand, if you take the moment generating function, take the derivative and set t equal to 0, you get the expectation straight away. The variance also can be very easily found out because you have expectation of x square, and if you subtract expectation of x whole square from this, you get the variance. Okay, now expectation of x is known from the first derivative, ex square is known from the second derivative, so the variance itself is found out very easily from these derivatives by setting t equal to 0. So this is there's a very convenient mechanism to obtain the mean and the standard deviation of a random variable. Now mean is called the 0th moment, first moment, and the second moment is the standard deviation. Nth moment can be found out this way. The third moment is called kurtosis. The fourth moment is called skewness. All this can be found out from the moment generating function. That's why it is called a moment generating function, because you can get all these moments which are mean, standard deviation, etc. of the random variable. Okay, this can also be seen by writing the Taylor expansion for e to the power tx. So if you take e to the power tx, then 1 plus tx plus t square x square by factorial 2, then plus t cube x cube by factorial 3, etc. Okay, so Taylor expansion of e to the power x gives you this quantity, and now expectation distributes over summation. So expectation of this quantity is 1 plus t into ex plus t square ex square by factorial 2 and so on. So by setting t equal to 0, you can also get, and also taking derivative of this Taylor expansion and setting t equal to 0, you can get all these moments. So that is the reason for the name moment generating function. So now let us look at the moment generating function of standard normal distribution. So standard normal distribution, mean is 0, standard deviation is 1. So the shape of the normal distribution, standard normal distribution, is e to the power minus y square by 2, 1 by root 2 pi. Okay, 1 by root 2 pi e to the power minus y square by 2. So, so this is the standard normal variable. Now, the moment generating function of standard normal variable is minus infinity to plus infinity e to the power ty, 1 by root 2 pi e to the power minus y square by 2 dy. Okay, the PDF multiplied by the random variable and integrating from minus infinity to plus infinity. So e to the power ty into e to the power minus y square by 2, the two exponents can be added. Okay, this is a to the power x into a to the power y, a to the power x plus y. So minus y square by 2 plus dy. So to that, I add t square by 2. Okay, I add t square by 2 and subtract t square by 2. So if I do this manipulation, then I can get e to the power t square by 2 out. Okay, and I have e to the power minus half y square minus 2yt plus t square. Is there some problem? I hear some sound. Okay, no, okay. So maybe somebody's connection has a problem. But this addition of t square and subtraction of t square by t, addition of t square by 2 and subtraction of t square by 2 maintains the equality So now e to the power t square by 2 is a constant. It can come out of the integration. And e to the power minus half into y square minus 2yt plus t square, that is e to the power minus half y minus t whole square. Okay, so this is a normal distribution whose mean is t and standard deviation, whose mean is t and standard deviation is 1. So this integration from minus infinity to plus infinity must be equal to 1, because area under any normal curve is equal to 1. So then the moment generating function for standard normal variable is e to the power t square by 2. Okay, so why am I doing all this? Because I want to show that the central limit theorem, which requires Sn also to be normally distributed. So Sn minus n mu by sigma root n, the moment generating function will again yield e to the power t square by 2, which means we will be proving that this quantity is also a standard normal distribution. Okay, so let us remember this very important result. The moment generating function of a standard normal distribution with mean 0 and standard deviation 1 is e to the power t square by 2. So you can verify that if you take the derivative and set t equal to 0, then the value will come out to be 0, showing that the mean of a standard normal distribution is 0. And if you take the second derivative and work towards finding the variance, you will find that this is coming out to be 1, showing that standard normal distribution has variance as 1 or standard deviation as 1. So I have shown the MGF of standard normal distribution. I proceed and look at the standard normal, the moment generating function of Sn star, which I am interested in showing is also normally distributed with mean 0 and standard deviation 1. So here is the proof. So expectation of Sn is n mu and variance of Sn is n sigma square. So Sn star is Sn minus n mu by sigma root n. I want to show that this is normally distributed. For that, I will show that the MGF, the moment generating function, is e to the power t square by 2. So here are the steps. First, I want to know the moment generating function of Sn star. So this is expectation of e to the power t Sn star. You have to multiply it by t and raise to e to the power. So expectation of e to the power t Sn star is e to the power t into Sn minus n mu divided by sigma root n, as per the definition of Sn star. Now Sn is nothing but sigma I equal to 1 to n xi minus n mu. So now I can now since so this is this summation, this t can come inside, okay, t into xi minus mu, and I can go from 1 to n. Mu is constant, so I going from 1 to n over mu will make it n mu. Okay, so these two expressions are equivalent. Now e to the power summation of few quantities is product of e to the power each of these individual quantities. So this is summation of I equal to 120 xi minus mu divided by sigma root n. So I can turn this into product of e to the power t xi minus mu divided by sigma root n. Now expectation can move inside product. Okay, that also we can prove, provided each of these random variables xi are independent. Okay, that also can be proved. So now this is product of expectation of e to the power this quantity. So this is again now each of these xi's are identically distributed, okay, with same mean and sigma. So I can take all these products and raise them to the power n. So it is a to the power x1 into a to the power x1 into the a to the power x1 up to n times. So I raise it to the power n. Then the next step is expectation of e to the power this quantity raised to the power n. I examine the quantity e to the power t xi minus mu divided by sigma root n. I apply Taylor series expansion, or the expansion of e to the power m. So this is 1 plus t xi minus mu sigma root n plus t square xi minus mu square by sigma square n, and so on. Okay, this is by expansion of e to the power p. So now expectation of this quantity, the Taylor series expansion, is E1 plus t into e xi minus mu plus t square e xi minus mu square and so on. Now expectation of xi minus mu is 0. This is expectation of xi minus expectation of mu. Expectation of xi is nothing but mu by definition. So mu and mu cancel, this is 0. And expectation of xi minus mu raised to the power 2 is nothing but variance, which is sigma square. So sigma square cancels. So I have now expectation of e to the power t Sn star equal to 1 plus t square by 2n plus 1 to the power n. Now I would like to study the behavior of this quantity ln, which is equal to 1 plus t square by 2n going up to infinity to the power n. And I am interested in knowing the limit of ln as n tends to infinity. So I take log of ln, this becomes n into log of 1 plus t square by 2n plus ... So n has come down, n into log of this quantity. This can be written as log of 1 plus t square by 2n plus ... divided by 1 by root n. So n into this quantity is this quantity by 1 by n. Now notice that as n tends to 0, the denominator gets to 0. And as n tends to infinity, denominator 1 by n goes to 0. And as n tends to infinity, log of this quantity tends to log 1, and log 1 is 0. So as n tends to infinity, both numerator and denominator tend to 0. This is a condition for applying L'Hopital rule. Okay, so I can do, I can apply L'Hopital rule. It is also, we call it L'Hospital rule, but L'Hospital is actually a Frenchman, and his name is pronounced as L'Hopital. L'Hopital rule. So the log of this quantity, numerator, when I take the derivative, it gives me minus t square by 2n square divided by the whole quantity. So differentiation of log of x is 1 by x into log of 1 by x into log differentiation of x. So this is 1 plus t square by 2n plus so on, and minus t square by 2n square. The differentiation of denominator is minus 1 by n square. Okay, now this is very nice. So minus 1 by n square cancels from these both places. Okay, minus also cancels. So I end up with t square by 2 divided by 1 plus t square by 2n, and each of the subsequent terms having n in the denominator. Now as n tends to infinity, the denominator here goes to 1 and leaving me t square by 2. So what do I get? I get that Sn star's moment generating function is also t square by 2. Who else has moment generating function t square by 2? Standard normal variable. Any standard normal variable has moment generating function t square by 2. This proves that Sn star, okay, this Sn star also is normally distributed with mean equal to 0 and standard deviation equal to 1. So central limit theorem is hereby proved, and this is a major step in our series of lectures. The central limit theorem statement and proof are done. Now we can believe the theorem and we can use it to our purposes, as it was used in, for example, the bridge problem. Okay, what is the total weight on the bridge? Normally distributed, because each of the cars weight is also normally distributed. And even if the cars' weights were not normally distributed, if the number of cars are more than 30, then this summation asymptotically approaches standard normal variable or the normal distribution. Very nice and very powerful, because all the instruments of normal distribution can now be used. So all right. So central limit theorem is now proved. So now our time is also up, about 5 minutes past 11. Are there any questions, comments from anybody? Any question? Am I audible, first of all?
Yes.
No,
Yes, sir.
I'm not. Yeah. Okay. No question. Okay. So this is one form of central limit theorem, but equally useful and many times more useful is the other statement, which is saying that the sample mean is normally distributed with mean mu and variance sigma square by n. Okay, and sample mean can be the mean or value of any quantity of interest, height, weight, nicotine content, accuracy value of the pause tagger, the precision value of sentiment analyzer, anything. Okay, just take the sample and deal with it appropriately. Okay, so I hope you have understood central limit theorem. So this puts us on firm ground in proceeding towards discussing test of hypothesis and test of significance. Okay then, so if there is no question, comment, then we will stop the lecture and meet you after 2 weeks with the testing of hypothesis, more concrete discussion. Okay, thank you.
Thank you, sir.
Thank you, sir.
Thank you.
Thank you.
Thank you, sir.
Thank you, sir.
Thank you.
Thank you, sir.
Thank you, sir.